So in the previous lecture, we proved that the range number of graph H is some constant times the number of vertices in H if the maximum degree of H is bounded. And then of course this C is function of this delta. However, in the proof we use the regularity lemma. So this is actually a power type function whose height is also a function of delta. So this is huge number. Okay, so we have a satisfying result that this sparse graph has small range number, but still this one is not optimal. This constant is too big. As I mentioned last time, we can actually improve this. And then how do we improve? We use the dependent random choice. So basically, what we did before using this dependent random choice to prove theorems on two-line theory, so we use it to find a copy of small graph H in graph G. Then how did we use it? We find U such that any, say, T number of vertices here as a large common neighbor. And if we find such a U, then when we have a bipartite graph H, then you arbitrarily put this into U, then no matter what vertices, so you have a vertex X and then you have its neighbor, say the three neighbor, no matter where those three vertices are, if they have a large common neighborhood, then this set is a candidate for embedding this X. If each vertex has enough number of candidates, then you can embed them all in a disjoint way. Then you already have a H. But this only allows you to find not so large graph here. But now what's our goal? We have G, which is two colored, and then we consider either red graph or blue graph. So that has this many vertices. And then in there, you want to find a copy of H. So if that has n vertices, then this H has n over C vertices. So it's linear size. So we want to find a quite large graph. So also we want to find such a U in a very large set. But the dependent random choice is not strong enough, and then it's not really true that such a large set have property that key vertex set here have large neighborhood. That's too strong condition. So what we can do is that instead of ensuring every T set has large common neighborhood, what we do is instead of every, we say many or most of. If we aim for this, then we can actually find such a U so that it has linear size. So in fact, let's use this. So let's prove this. So how do we do this? So let's say you have a G will be your either red graph or blue graph that has many edges. So let's specify the numbers first. Let's say epsilon is positive, then delta and n are the natural number, and let's say n prime is also a natural number. And if n prime is 1 over 8 times 1 over 8 delta times epsilon to the delta n, and assume that the delta is at most n prime. So assume you have these numbers satisfy this relation. Of course, I mean, you might think that this might not be an integer, but in that case, you just take a floor or ceiling accordingly. It's not too important. You just round up as if, I mean, as it makes sense. So, when we have this parameter, if G is an n vertex graph with, say, epsilon n square lattice, then what we want to do is that find the set U. There is just set U which has large size, at least say 2 times n prime, such that most of the set has large common neighbor. So at most, say the number of sets with small common neighbor is 1 over 2 delta to the delta times that's the fraction. So out of all subset of U of size delta, only this fraction of the sets satisfies that its common neighborhood is small. And here small is smaller than n prime. So you can prove this by using dependent random choice. Because how did we prove dependent random choice? We will mimic it. So we randomly choose delta vertices. Say V1 to V delta are random vertices in the graph, which are chosen independently and random. And uniformly random. Meaning that you choose V1 uniformly chosen one vertex. So out of n vertices, each vertex is chosen with probability 1 over n. You choose one. And second one, you do that. Third one, you do that. It's independently chosen, so first vertex and third vertex could be same. It doesn't matter. And then we let U be the random set which have common neighborhood of this. Say P1 to P delta. So you consider this set and then you take a common neighbor. And then let X be the random variable counting the number of vertices in this U. Then what? You can compute the expectation of this X. And then that guarantees set U of certain size. And then we later compute the probability that each subset of U actually has large common neighborhood. That's roughly how the proof goes. And let's compute the expectation of X. And then let's denote this as mu. The mu is certain number. So what? For each vertex in G, the probability that it's in U can be computed. And what's that? This is computed if you have its neighborhood, and then if V1 is here, V2 is here, and then all V delta is here, then this is in U. If one of them is outside, then this is not in here. So what? You take the degree of B and then divide by N. You have to multiply that to itself delta times. And that's the probability that we are looking for. And what this can be written as the degree sum of the degrees of the power delta, degree to the power delta. But what's this? That's the average of function fx is x to the delta, then average of the function, and by convexity, we know that this one is at least you take the average and then apply the function. But what's this? We assume that it has at least two epsilon n square edges. So this is at least what? 2 times epsilon n square over n. So you compute it and what? It is at least epsilon to the delta times n. Okay, so this is good. And then now we compute the number of bad subset of U. Bad in a sense that this satisfies. It has small common neighborhood. So let Y be the number of all subsets of S. Subsets S of U with the size delta that has small neighborhood. Small common neighborhood. Common neighborhood size smaller than n prime. Then what? We can compute the expectation of Y. Let's say that's U. How do you compute it? And that's like for all subsets, you add the probability that this one is counted by U. So for a given set F of size delta, which is bad, its common neighborhood size is smaller than delta prime. What's its probability? Probability of this one is subset of U is what? Again, same way. S has small common neighborhood. The only way that this S is inside of U is that P1 and P are all in this common neighborhood. So this is the probability. And this is what? You take and choose delta many. So number of bad sets is at most n choose delta. And this is what? N prime over n to the delta. So this is an upper bound on U. So this X is a random variable, but this mu is an expectation. This is actual number. Y is a random variable, but its nu is also expectation to be computed. It's a number. Then what can we consider is this expression. This is random variable. So X give you a random variable, and then once you obtain a number according to your random experiment, you take the delta's power, and then you just compute this as a number, mu to the n over 2 nu times y. The y is random variable, but this is number. And then mu to the delta over 2. So you consider this random variable. And you can compute the expectation of this. And what's this? By linearity of expectation, you can compute this in this way. And again, this function f of x equal x to the delta is convex. So this is like you apply the function and then take the average. And you can do the other way. You compute the average and then take the function. Then this one is smaller, so you can replace this with this as a lower bound. And what's this? This, you know that its average is mu. This is mu to the delta minus mu to the delta minus delta over 2 minus mu to the delta over 2. And this is non-negative. Okay, then what does it imply? This is a modification of a method, the deletion method we use. And this means that this implies that in our random experiment, there is an outcome, there is a choice of this B1 to B delta, and corresponding set U satisfying this inequality. But what we know is that each of these terms are always non-negative. This being at least 0 means that this one is bigger than this, and then this one is bigger than this. So we know that x to the delta is at least mu to the delta over 2, as well as x to the delta is bigger than mu to the delta over 2 mu y. So in other words, you can write it as y is smaller than 2 times mu times x to the delta divided by mu to the delta. Okay, then we have these two properties. What does the first properties give? X is a random variable that counts the number of vertices in U. So that means U contain at least what? You take the 1 over delta power here, then that's at least mu over 2. Actually, this 2 can be written as 2 over 1 over delta, but we don't gain much, so it is already enough. It is n prime. No, sorry. This is at least 2n prime. Why? What does mu? Mu is this. Mu is at least this, and then n prime is this, so it's at least twice of this. And also, but you know, y is small, that means what? This is 2 times x to the delta mu over mu to nu over mu to the delta. But what does this mean? This x measures the size of u. And what's nu? Nu is this one. So this is most that one. So n choose delta times n prime over n to the delta. And then this one is what? 1 over epsilon to the delta square times n to the delta. Okay. So this one is what? you can take, so this is what? This is like upper bounded by n to the delta over delta factorial and u to the delta. So this give you u choose delta as an upper bound, and this cancels out, and remaining parts are n prime over epsilon delta n to the delta, and then technically this and this one is a bit smaller than that, so you have to like take 2, but let's put everything inside. So this is an upper bound. Then what? You know n prime is defined in this way. So all the other terms could cancel out, but this term survive. So you can actually show that this is at most like this choice. So that means the resulting U satisfies that what U counts out of all subset of U with size delta, the ones that has common neighborhood size too small is small fraction. Okay. Here, actually, I mean, we also use the fact that if U has size at least 2 times n prime. Yeah. Anyway, it's just computation. So what you have is this as well as this. That's what we are aiming for, and this proves the lemma. So using that, we have this lemma. And once we have this lemma, now we can use it to prove the statement that we wanted to prove about the lambda number of age. And maybe it's good time to break it here, and then I will continue doing that in the next video.